So as promised, I'm going to show you how to finish the problem if you decided to use the first derivative test. So our critical value was 100 times the square root of 2 over 23. We would need to set up a number line or a chart that includes our domain. Actually, I'm going to make this an open circle because we didn't include 0. And I'm going to plot my critical value on it. Now I need to test values to the left and to the right of this. So I'm going to pick something really simple like 1. So the derivative, just in case we forgot, was 115 minus 100,000 over x squared. So when x is 1, c prime of 1 is 115 minus 100,000, which is a negative number. Remember, I only care about the signs of these numbers. So this guy is negative. Now I need to pick a value over here. So I'm going to pick 100. So c prime of 100 is 115 minus 100,000 over 100 squared, which is going to be 10,000. So 115 minus 100,000 over 10,000. So this gives me 115. 100,000 divided by 10,000 is 10. So we get a positive value, and so we know this is positive. So if we read this number line, we can see, and we want to make sure we label this as c prime of x, we can see that this function was going from decreasing to increasing. So this is a relative minimum. Once you've just stated that it's a relative minimum, you can then verify that it's an absolute minimum by making the same statement as before, right? So since there is exactly one critical value on our domain, then x equals 100 times square root of 2 over 23 must be an absolute extrema. So we can then plug in the values, find x and y. And we're done. So you can see the point I was making on the previous video. Both of these would get you to the same final answer, but we should hopefully be savvy enough now where we can kind of see if a function, if taking the second derivative is going to make life better or worse. The advantage to the second derivative is we only had to plug one value and look at the concavity. The first derivative test here we had to plug 2 values in. So if you're dealing with a function that you can just use the power rule for, it might be better or in your favor to do the second derivative. If it's something that requires like a quotient rule or a product rule, then the second derivative could actually get more complicated and it might be a lot harder to plug values in. So just use your best judgment, but both paths will get you to the correct answer. If your interval on an optimization problem happens to be closed, well then we could just use the closed interval method by making that table of values that by default returns absolute maxes and mins, and we wouldn't have to use first or second derivative tests. So I'm going to add here at the bottom for open intervals, right? And these are our domains. You have to use first or second derivative test to verify type of extrema, then you have to confirm that you have an absolute extrema before you can proceed with the problem. Closed interval, you simply use the closed interval method. And we had a previous problem on this final where we asked you to do the closed interval method, so you can go back and review that if you're not sure what this method looks like.